Okay, good morning and welcome everyone for joining us for this workshop on how the robot operating system can be used as a community to help better integrate radiation sensors with our robots. Just a polite reminder, I think all of you have already, but if you have a microphone or camera, just switch them off for this first portion of the workshop, but you will need them for later on. So let me introduce myself. I'm Andy West. I'm a postdoctoral research associate at the University of Manchester, and I'm with the Robotics for Extreme Environments group there. We're interested in deploying robots into places where humans wouldn't go. So that includes places like electrical substations, mines, offshore wind farms, and of course nuclear environments, which is what I'm interested in my research. And today I'm joined by Alex Smith, and I'll let him introduce himself.
Good morning, everyone. I am Alex Smith. I'm at the Bristol Robotics Laboratory Research Fellow on the National Centre for Nuclear Robotics Hub. We're mainly looking at robots and nuclear decommissioning, and like the main thing that we've been working on is sorting nuclear waste, particularly intermediate level waste and low level waste. So nuclear sensing is important for that. We're aiming to try and automate the process and make it a lot faster.
Cheers, thanks Alex. So we're both interested in robotics for nuclear environments, sort of different aspects of the same challenges. And we put this workshop together because essentially we were encountering a problem. And that is that each university or company or industrial user has been slowly integrating radiation sensing onto robots. But when we want to try and share this technology, our hardware or our software, it just isn't speaking the same language. And then a lot of effort is going into rewriting drivers and algorithms, trying to meet in the middle, and that seemed like a total waste of time, basically. So we want to be able to add, swap, upgrade radiation sensing capabilities and the algorithms that go with them without all this hassle. And standardization is a key part of that process, and that's why we're here today. So thank you again for being here this morning. You all actually represent a really broad range of interests. We have instrument manufacturers, we have industrial users, we've got academic researchers, and that's exactly the wide-reaching participation that we wanted to have today, and hopefully it will lead to some really solid outcomes. So, sort of a bit of a breakdown of today. We're gonna, for some of you, you may not be familiar with the robot operating system. For some of you, it will be, you would have heard it all before. But we'll talk a little bit about ROS and why we're interested in it as researchers deploying these robots. The current landscape, or just like a very brief impact into the sort of radiation sensors that are currently going onto robots. That should hopefully take no more than about, hopefully about 40-45 minutes. We'll take a little break and then about 10-15 minute break, and then we'll get onto the group discussions. And then in the group discussions, we're going to split you up. You guys can sort of discuss the problems, the challenges we're going to present to you today, and then we're going to come back and we're going to try and hash something out between us in terms of getting towards standardization of this issue. So let's get started. So what is the robot operating system? Well, it is a popular solution to quickly adding hardware and software together to build up robots that can do a job that's required. So the term operating system is actually not really true. Instead of it, it's more of a, so people call it a middleware or a framework to standardize how information is moved around, really. That's what it is. So we talk about an operating system, but actually ROS runs on Linux. The sort of next flavor of ROS will run on Windows, will run on Mac, will run on, even run on microcontrollers. So don't really think of it as an operating system. It's a bit of a misnomer. And it's not that scary. Everything's written in C++ or Python. To be honest, there's a workaround for nearly any language you can think of, into programming language you can think of. Really, its biggest selling point is that there exists all these different bits of hardware and software that you would need already out there. So let's say you're developing autonomous vehicles. Someone has already made you a pedestrian detection algorithm, right? Maybe you need to build maps and navigate through unknown environments, like in the nuclear sector or a hospital or whatever. Someone's already written a nice bit of code for that. Fantastic. And also if you need hardware, so let's say you need a laser scanner, you need a LiDAR that can plug in and just work for obstacle avoidance, that's available too. And all of it's open source, and manufacturers and researchers have enabled people to just get on with what they actually want to do rather than having to reinvent the wheel. And everything is pretty much plug and play. A nice thing about being open source is that all the software can be sort of interrogated and tested and checked. I'm sure we've all been familiar when we've been given some black box, some like locked down bit of software with maybe bugs, and we don't know why it's broken for some reason. The nice thing about ROS is there's this transparency as well, which you can imagine for a regulatory body or an auditor. That's a really nice thing to have. Finally, it includes.
What's up, everybody? This is Danny Bearden.
It includes all free open source physics simulation environments. So you can essentially build and develop your own robot without ever needing to build the real thing. You can do it all in simulation, and you can test all your algorithms and what have you. As an example, Amazon recently released an entire simulation of a hospital for people to test and develop robots for in response to COVID-19. Because you don't necessarily want real robots running around hospitals whilst you're, developing these things. So ROS is not just for academia. It's used by the likes of Amazon, Bosch, autonomous vehicle manufacturers. NASA are even using this on their for their robonauts, so their robotic astronauts they put on the International Space Station. And it's already been demonstrated in nuclear facilities as well. So this is already out there and being used in the nuclear sector. So the philosophy behind ROS is that you need some functionality. You just then grab an existing solution, or you can make your own. And you can then plug it into other components in the system to build up a whole, whole robot with its capabilities. So in this example here, we've got a mobile robot with an arm on top. So first, we want to tell the robot to move forward and just do it. So the nice thing is if the manufacturer has made a ROS compatible robot, that's all done for us. Out of the box, we can basically drive this thing around like a remote control car, but we probably want to do more than just have a glorified remote control car. So let's say I want it to avoid bumping into things. Maybe this is working in a warehouse. So I use a laser scanner, I use a LiDAR sensor, which is ROS compatible, and stick it on the front of the robot. I then add some off-the-shelf code, which means it can now navigate and it can avoid obstacles, drive itself from A to B, and that's great. Then we have the arm. So the arm is meant to pick up objects in our warehouse. So a basic webcam can be used, and then we use some snazzy object recognition. And that way the camera can also be fed into using the arm, but perhaps we can also use the camera to help identify more obstacles, or maybe humans. Maybe the camera is very good at detecting humans. So that camera can go two ways. That data can be shared between both navigation and the object recognition. So all these different parts, so wherever I have a box, in ROS we would call these nodes. So I have nodes which are nodes which are essentially connected into multiple other nodes. And the nice thing is that if we want to change this in any way, it's very easy to do so. So let's say the camera, it's like a cheapy webcam, and we actually want to do better. So we change the camera. And if you see, basically everything else stays the same. The object recognition and the navigation doesn't have to change just because we changed one part in the system. We don't have to mess around with anything else. It's literally just plug in a new camera. But whilst we're here, we might also decide that we didn't like the path planning algorithm that we were using, because of course it was just off the shelf. Someone else wrote it. Maybe we've got a better idea of how it should be done. So maybe we swap it out for a different kind of path planner. Now, let's also assume that we want to sort some nuclear materials, or we were saying, in a in a warehouse. And imagine we want the arm to separate nuts and bolts. They're the two things, pretty simple, just separate nuts and bolts. So we've got object recognition, and then maybe we write our own bit of software, a little algorithm that then says, take the bolts and put them in this box, take the nuts, put them in that box. And then we can feed that into the control of the manipulator, the arm on top. And so we've been able to sort of inject our own functionality in, whilst just grabbing other stuff that other people have made without having to waste time, which is really, really nice. So the question now is, how does ROS manage this interconnectivity between nodes that allows us to just just chuck things in however we like? Well, each packet of data that's going back and forth, a so-called message, has a very defined structure. So both parties, both nodes, know what to expect in terms of the data that's being shared between those nodes, and that's how they handle it, and it's the so-called ROS messages. And that's really what we want to focus on today. ROS messages are based on the information that they wish to convey. So in this example on the slide, we want to convey temperature. Now, it doesn't actually say if it's ambient temperature or the temperature of a motor, or maybe it's the temperature of a component that you're monitoring. Regardless of the application, the message would look the same. So there's a defined structure, and that's how ROS basically knows what to expect when we pass it over. So in this case, we have three fields. So we have the header. This is pretty standard. You don't need to worry about this too much, but that basically has its metadata. So it'll be a timestamp of when the node sent the message. Something called the frame ID, which basically says where was the temperature taken. So imagine I had a sensor on the front of the robot and a sensor on the back of the robot. Essentially, the frame ID says this was the one from the front of the robot, which is at 10 centimeters at the front of the robot. Basically, it's figuring out where you are in space. But then we get to the good part. We get to the actual temperature. So notice that temperature here is in this little comment. So you've got the hash, and that's then a comment. The temperature is in degrees Celsius. So ROS as a default uses SI units. But the more important thing is that any node, hardware or software, knows that we're talking about degrees Celsius, which is also important, right? We don't want to get confused converting between Fahrenheit or whatever, or Kelvin, which may cause our system to malfunction in some way. There's also this variance value, but we don't really need to worry about what that is. Basically, that's just another number telling you how the variance, if you like, is just a statistical number. And as you can see there, if you just leave it as 0, it's ignored. So notice as well, we have the header, we have the temperature, and we have the variance. And on the left-hand side, we also have what says header, float 64, and float 64. So as well as knowing, so it has a defined structure. There are 3 fields called header, temperature, and variance. They also have a set data type. So in this case, because temperature is a continuous value, what we do is we send a floating point number of 64 bits in length, or precision is 64 bits. And that way both parties also know what the data should look like as well. So you know that you're dealing with floats or you're dealing with integers or whatever. And ROS has some standard data types that it uses. So I'll very quickly gloss over this. So Boolean operators, so true or false. Integers, so that would be whole numbers, and you can basically pick 8-bit, 16-bit, 32-bit, or 64-bit. So, you know, more bits, the bigger the number you can have. Unsigned integers, so if you don't need the minus sign. Floating point, so floating point would be for continuous values, so where you need a decimal point. Once again, that could be 32-bit or 64-bit, depending on the precision that you need. We then have strings, so if we want to send, you know, a list of characters, you know, the classic would be hello world or whatever, or maybe it's just a firmware version that you want to write down, or you know, gosh knows, you might want to send a string. In this in the header, you remember I said that there was a timestamp. So time is defined as basically the number of seconds, and then you can have the decimal, and then that gives you the number of nanoseconds. Since so if you're dealing with dates like absolute time, then it's the so-called epoch time. So it's something like the number of seconds which have passed since the 1st of January 1970. It's what Unix machines use, and that's just the standard that they've chosen. But you can think of time just being always in seconds, basically. And finally, a neat little thing is that you can have arrays of these. So you don't just have to have one floating point value, so say temperature. Let's say an image is it's an array of by height and width. It's an array of height and width of integer values normally. So you can have that array, so you don't have to send an image 1 pixel at a time. You can send it as a whole image using these arrays, and they can be either fixed length, so the code knows that you're going to send 3 values or 5 values or whatever, or it can be variable. So for example, with an image, because you might be changing the camera, you don't want to lock in the number of pixels because different cameras have different number of pixels. Okay, at this point, I'm just going to take a few seconds and just ask if anyone has any questions before we continue. And I'm also going to take this as a tactical moment to have some coffee. I know that was incredibly quick. For those of you who are already familiar with ROS, you know, this will be old hat, but obviously some of you, obviously for some of you, you're not familiar. So this is why we've gone through it. So why would you need 64-bit float for temperature? Good question. So the temperature message comes from this. So in the same way that I said that you can grab software and whatever that already exists, the temperature comes from an existing set of messages that just come with ROS called the sensor messages package. And this is basically universal, and that includes things like how LiDARs, how laser scanners work, cameras, whatever. I agree that 64-bit seems a bit over the top. I imagine when the Open Source Robotics Foundation designed these sensor messages, they probably wanted to give people the better precision that you would get with 64-bit. I personally can't think of an example where you might need that level of precision. Maybe you're measuring how hot the sun is or something in Kelvin or something, but yeah. So actually, Yannick, you touch on a really good point, is that if 32 bits will do the job, then why bother going to 64-bit? Okay, a question from Michael. What is the resolution on time/duration? Is it really nanoseconds, nanosecond? Yeah. So it is actually, so it is seconds dot nanoseconds. So typically what happens is that it will be the timestamp at which the computer basically will make some, well, basically the computer says, what time does my clock say now, or what does the clock that ROS is referencing say, and then grab that. So probably you can't trust, you can't trust the end few digits on those nanoseconds. But what it does allow you to do is measure, probably you can trust it up to the microsecond range. So I would trust the processor in my computer, or even on a microcontroller, to go, milliseconds or microseconds, which might still be of an importance. That second dot nanosecond is once again a format which they've decided to go with based on this Unix epoch time. Another thing I should say is ROS itself, well, the current implementation of ROS, or your standard implementation of ROS, is not real time. So actually these timings might have a little bit of skew to them anyway, because often you're running on Linux or Windows or whatever, which is not a real-time operating system. So that's just another little thing to consider. But genuinely it is, you are measuring the number of nanoseconds. Okay, another tactical coffee. Thank you for those questions. Right. So really what we're here today to do, or to try and do, the aim is to try and define some ROS messages which will allow us to easily integrate and change radiation sensors. So what we're going to do now is take a brief look at what radiation sensors might look like, what is already being used on robots currently, then we're going to look at maybe what the future of radiation sensing with robotics might look like, and then we'll have a little catch up again. We'll have another one of these little questions sessions. So, we don't want audio. Let's mute that. So in the top left, we have this sort of this green and red sensors. These were attached to Karma, which is actually the video next to it that's playing along there. And Karma was the first fully autonomous robot on Sellafield. So Sellafield being the UK's largest nuclear facility, in the United Kingdom. And it was equipped with this paddle for alpha-beta monitoring, so checking any contamination on the floor. So that was a solid state detector. And then it had a Geiger-Müller tube in this rad IG-10 that was measuring for gammas. So these are essentially personal dosimeters which have been used in the industry, which were retrofitted to talk to the robot. Now, in the bottom left, this was the first robots that went into Fukushima after the tsunami and everything. They didn't necessarily have the luxury of these integrated radiation sensors, and neither did they really have the time. So they took these electronic personal dosimeters, this little blue stick, which were just used by the staff, and just strapped them to the robots. So these are sort of solid state detectors, and all they did is they pointed a camera down at the screen and then just read that back. And I think we can all agree it would have been nicer if actually that sensor could talk to the robot. because you can imagine as an operator, you're having to try and figure out, you're trying to look at a camera and it's a bit of a mess. But the point I'm trying to make is that actually really the start of robots with radiation sensing has just been using existing sensors that people are, that industry are just using day to day and just strapping them to robots. Now that has got a bit more sophisticated. Well, it has got more sophisticated as we've managed to get them to talk to robots. If we look over in the top right, there's a small Chromec device that's been attached to an aerial vehicle. Might call it it was a fixed wing vehicle, and that flew over Chernobyl. So in the fields, I think it's called the Red Forest around the Chernobyl reactor. That aerial drone was able to basically map contamination or at least hotspots of radiation using this Chromec detector. So you can see it's very compact. That's basically a USB port at the back. You can see how small these things are getting. And this one on the bottom right, this is a scintillator type detector. Once again, you can see how compact it is compared to this pound coin. And that was attached to a robot, part of the Tyrone project. And as far as I'm aware, it's the first robot to survey an active nuclear reactor, as far as I'm aware. But these two guys on the side, on the right-hand side, are actually doing spectroscopy. So the ones on the left, you can see you've got the two at the top. So one is talking about microsieverts per hour. So that's on the gammas. You've then got 3.5 counts per second. So these two are basically they're not interested in the energy resolution. You can even see in the one at the bottom from Fukushima, they're talking in millirem dose. So some of these the top ones are time resolved, per hour or per second, and the bottom one is just total. The ones on the right are actually, as well as doing counts, regardless of energy, they're also splitting, they're doing spectroscopy. So they're splitting the events that they see based on the energy. Now, not only are they doing more sophisticated things as detectors themselves, but this information is getting fed into other parts of the robot. So as you saw with Karma, it's driving around and it's making maps. We have this little GIF in the middle here at the bottom where the radiation measured by the scintillator detector has been projected onto a 3D reconstruction of the environment. So this hopefully is starting to get a flavor of, it's not just radiation for radiation's sake. The radiation information can be used as holistically as part of a bigger, greater robotic system. So this is currently where things are, but things are moving quickly. Oh, that is muted. Good. So both on NCNR and both on RAIN, so these nuclear robotics hubs, big nuclear robotics hub in the United Kingdom, we're interested in teleoperation with manipulators. Can we remove humans from having to put their hands in glove boxes or to try and manipulate nuclear materials manually, and instead remove the human, put them in a safe location, and have things remotely operated, teleoperated? So that radiation information could be really useful for an operator to know what's radioactive, what's not radioactive, how can I sort and segment that waste based on the task that I'm trying to do. And this sorting and segmentation, so the government only last month, the UK government only last month announced a £4 million competition to autonomously sort and segregate nuclear waste. So really, I'm talking about future needs of radiation sensing. This is not far future. This is very near future requirements. And this automated, you can think of automated systems not just arms, you can think of it as these large integrated systems. So maybe you have something measuring vehicles as they enter a site. They then go to a docking bay. The vehicle, it might be even an autonomous vehicle. The autonomous vehicle drives up to a bay. It then unloads some materials. There's then conveyor belts, which are then sorting and segregating waste or whatever, and there's no human here at all. So the radiation data that we're collecting is not just for mapping or dosimetry. It might be used for much more abstract tasks and challenges that robots want to achieve, and what we want to achieve. So just a few notes or things I want you to think about before we go for a little break. So there are some, clearly in radiation sensing, there are some common units, and we saw these on these different detectors. So for example, counts per second is a very common unit, but it's not strictly an SI unit. So we need to think about, we might need to break normal ROS convention to provide something which is going to be useful for both the robot and humans. We see also that we're talking about total dose versus the rate. So there's also a temporal aspect in here. So what we're measuring is not always the same. Even on the same detector, it might have a total dose functionality and a rate functionality. Both of those are interesting for robots and humans in different ways. And also we have absorbed versus equivalent dose. So I've seen sensors, and hopefully you'll be able to discuss this in your groups, that sometimes sensors will report things in gray. So then, essentially not corrected for based on the radiation type, or sieverts. And to be honest, I think most will report in sieverts rather than grays. But of course, if you're talking counts per second, all gets a little bit confusing. And there's a lot of scope, and obviously that's one of the things we want to discuss here today. Types of radiation, this is a big one. So different detector technologies or different designs of detectors will measure different things. So we saw earlier that we had these alpha beta sort of paddles, like handheld paddles that we were sticking on robots. You might have sensors that are sensitive to only gammas, or sensitive to gammas and neutrons, or gammas, neutrons, and X-rays. Is this important for a robot or important for a user? That's another question. So when we're trying to communicate this information, is that something that we need to highlight? And finally, what are these sensors being used for? I think this goes back to things like rate and total dose. Is it just, is it that we're going to look for a count rate, which is going to feed into a yes or no, and the arm is going to go, if it's yes, it goes one way, if it's no, it goes the other. So try and think about what sort of data do these systems actually need to get the job done, and what activities you might expect them to see them in, and what information do you need to achieve that task. Okay, whew. So I've done a fair amount of talking. So what we'll do is before we break, I'll open everything up for questions. So whilst you're writing out any questions you might have, I'll just give a little brief overview of what's going to happen. So we'll break for 10 minutes, 10-15 minutes. Go grab a coffee, answer emails, run to the loo, whatever you have to do. Whilst that's happening, myself and Alex are going to break everyone up into little discussion groups. When we come back, we're going to come back, we're going to just discuss a couple things, and then you'll be broken out into your different groups, your rooms, these breakout rooms, where we want you to discuss what these ROS messages might look like and what's the information that's important. basically, we'll run through that. We'll get everyone back and we'll discuss this. But we'll cover this again after the break. So at this point, we're open up to questions. So if anyone has anything they want to mention, please feel free. And I will take this opportunity to have some more coffee. Okay, that's great. So let's aim to come back at 25 past the hour, where we'll reconvene and we'll go over a few things. Oh, okay, we have a question. Marty jumped in just before we broke. Is the goal to request a ROS enhancement proposal to the open source? Ah, okay, so that's a good question. So at the moment, I think this is probably too niche. What I would like to see is actually other fields getting involved. So maybe the human-robot interaction community, maybe the agriculture community coming together, making some of these messages, which is important to them, maybe as part of the UKRAS network. That would be nice. And then maybe we say we have a bunch of messages. We're going to call them instrument messages. You know, we already have sensor messages. We already have common messages, standard messages, sorry. And we say, look, we have this proposal for these instrument messages that we as a community would like. Do you want to put it out there? For the time being, though, this will go up. Any messages that we produce will go up as a package on GitHub. We'll figure out who's going to host that. It will either be Manchester or maybe UKRAS has something that we can use, and we'll make that freely available. Try and promote that as a package, and then people can use those radiation messages in their work. That's the hope. There's been a lot of interest in this workshop, a really surprising amount. So I think there's a lot of scope for other fields, as I say, e-agri, human-robot interaction, what have you, to actually sort of to copy this and become a larger force and maybe push something to the Open Source Robotics Foundation. But cool. Thank you for the question. Okay, cheers, everyone. Right, we will start the break and we'll see you at 25 past. Okay, welcome back, everyone. Let's get back into the presentation. There we go. So before we get started, just wanted to say a few notes on how these ROS messages are constructed. Because hopefully what we want you to do is be able to sort of start designing these structures as well as what you think the data types should be. So let's have a look. So ROS messages. So one thing I want to say is ROS messages can be nested. You can have these sort of compound messages. So for example, if we look on the bottom left, we have pose. So I've kind of, this is it's a little bit different from the real one. But you can see that there's two fields called position and orientation. And each one of them is made up of three fields, X, Y, and Z. And then for orientation, I've got Robert Yaw. So because you can have these multiple fields, you don't have to. So you can imagine for a pose message, there already existed a position message and there already existed an orientation message, and then they stuck them together. So if you think there's already existing messages which may be able to be well suited to this in either common message, standard messages, geometry messages, whatever. If you're familiar with ROS, then obviously don't reinvent the wheel. The header field is it's really common. We'll probably want that in a ROS message. So as well as giving the timestamp, it also gives you the location relative to another part of the robot. So I said earlier that you might have the robot, you might have a radiation sensor mounted to the nose of the robot. Maybe it's looking for contamination on the floor. And you would say that frame is 10 centimeters in front of the robot, and the robot has GPS coordinates, or it has its own LiDAR coordinates. And it basically means that you can go, it's like that song, like the wrist joint to the elbow joint to and eventually you can get from anywhere, you can get to anywhere else, essentially, in terms of position. So that's probably going to be useful when we consider if we want to spatially resolve this radiation, which we normally do. And temporally as well. It'd be interesting to see how radiation changes over time. So the timestamp is really useful as well. Finally, this sort of device-specific messages versus global messages, I want to just touch on it a moment. So some hardware and some software in ROS do offer their own custom messages like we're talking about now. But they normally do it to add additional functionality. So a common servo motor that's ROS compatible is a so-called Dynamixel servo. And that actually sends two different types of messages at the same time. So one is its own message, which is a Dynamixel servo message. And you can see that has 51 fields. It's massive. It's clearly a lot of information that has to be sent every single time. Some of this is important, but actually there aren't many other nodes that need all this information. And in ROS, really what we want to talk about is the state of the joint. So at what angle is the joint at? And that is conveyed with a so-called joint state message. And you can see a joint state message is only 5 fields. It's literally 10 times less stuff being moved around. So there might be some really specific things that on your sensors you think is useful, but don't let it lock you in. There's nothing stopping us having multiple messages. One, if you're designing your own instruments in your own universities or businesses, don't let this constrain you, is what I'm saying. But we want to make it so it's a standardized message that everyone can use. So it should be flexible, hopefully simple, and not too bloated as well. So before we go in, some things that I'm gonna hope that you guys can think about. What information is important for radiation instruments, and think about the applications as well. Hopefully some of you have been using these sensors and can talk about their applications. Try and make these messages descriptive enough to convey the relevant information without being too unwieldy or too detector specific, like we saw with those servo motors. Another little aside is there's something called the ROS parameter server. It can also hold information, but typically it's information that doesn't change. So, for example, you might not want to send the serial number of the detector every single time. You can sort of put that aside on this parameter server. So when everything starts up, you just sort of populate that parameter server. So make the assumption that though another node should be able to accomplish the majority of its needs within one message. If the serial number is going to be an integral part to a lot of algorithms, then include it in the message. There's an obvious need, or I think there's going to be a need for different messages to convey different types of information. And multiple messages are okay. But remember that when nodes are written, more specifically in Python, you can get around it in C++. These nodes expect a specific message type. And this is what underpins ROS. And the problem is going to be if we have sensors that, they have maybe 3 or 4 different types of messages, then you're going to end up having to rebuild your algorithm 4 times or whatever, just in case of whatever the message is. So yeah, if there's loads of messages, this idea of simply swapping sensors starts to break down a little bit. So we can have multiple messages, but it's got to be justified. And I think there are some arguments for having different messages in there. Think also, are there any existing messages that can do this kind of information? So often so for example, Fukushima, radiation has been superimposed on images. So as just color, so sort of like a green to red scale. That can be achieved with an image message, for example. We were talking about doing spectroscopy earlier, but spectroscopy itself is quite broad. You might be, if you're talking about optical spectroscopy, you might be talking about wavelength. If you're doing Raman shift, you'd be talking about wave number. If you're talking about, gamma spectroscopy or neutron spectroscopy, then obviously we're talking about energy. But the format of them is all the same. Essentially, you have a 1D array, which is referenced to an energy or a wavelength or something. So if you think there's scope for a message that could cover not just ionizing radiation, but perhaps could be broader, then do let us know, because it might be something that other people are interested in for their work. Okay. Right. At this point, I'm going to hand you over to Alex, who is going to essentially facilitate this discussion part of the workshop. Thank you, Alex.
Cheers, Andy. So I think what's going to happen is we've allocated you all into breakout rooms. When you get kicked out into those rooms, I think probably a good start would be for everyone to introduce themselves to each other. There should be a good mix of university and industrial people in each group, hopefully. And if someone can take the role of leading the discussion just within the group, I think we'll do about 15 minutes, Andy? About 15 minutes, yeah. And I'll check in on you about 5 minutes before you've got to finish and just see how you're getting on. And then we'll come back in and we'll sort of go through whatever everyone's sort of talked about and try and build it up together. So I think good to go? Cool. All right. Catch up with you in a minute. Okay, I think someone starting to come back in now, I think.
Yeah, we're back.
There we go.
Here we come. Is everyone back in now? We're waiting for, oh no, is everyone? I think that's, yeah, everyone's in now. Okay, cool. So what I'm going to do is hopefully you have someone to speak on behalf of your group. And what we'll do is we'll just go through anything you've discussed really and you want to add to the discussion, then we'll just put it all down and then we'll collate at the end and try and get something useful out of it. So can I start with group 1, which is Dom, Francesca, Michael and Thomas? Someone?
Yep, hi, sorry, start video.
Hi.
Hi, so we had a, do you want to tell me what you want from me first?
If you go ahead and just anything that you discussed about which you thought was important.
So we spent some time trying to think about what we'd want in a sort of radiation message, of which the sort of things that we came up with were having a header is obviously important, so you can locate where the sensor is.
Okay.
And then because it was something that was difficult was trying to understand what all sensors need. So because some are obviously single measurements and some are spectrums. So then we said you'd have a way of defining if it was a single measurement or a spectrum. It's that's just a bool in some way in the message, and then you'd have some of the bits of information being the particle that you're trying to detect. So alpha, beta, gamma, or even more specific. Say you've got a certain isotope.
So is that something like having a Boolean for just saying if it's alpha?
Yeah, because then it would just be what you're detecting. So it's particle type, and then you'd have either, I think we called it quantity, which was like a single measurement, and then a spectrum as well. So you fill out either one of those depending on if you're doing a single measurement or a spectrum of everything. And then you need some way of describing the spectrum, but I don't know enough about those. Some way of saying it's this wide and it has this many bins or.
Yeah, that's okay. Hopefully there's people that have used these sensors a bit more often and can give us a better idea of what the kind of data that gets spit out.
And units as well. Units is important.
Would that be do you think that would be a string?
We didn't discuss that, but some way of defining units would be useful.
Yeah. Is there anything else?
What's this? I said header, so particle type, units, and then single versus spectrum, and then a quantity for a single unit and a spectrum for a spectrum. That's,
cool.
That's most of what we discussed.
That's cool. That's good. Group 2, if you know who you are, it's Yar, Marty, Matt, and Binor.
I might talk about this one. But yeah, I think we had a similar sort of thing. We were wondering if it's going to be two different messages, your kind of single data stream type thing, and a spectrum, because they might be two different, so maybe including the same. But there was like a big difference between the two, and then only a lot's been covered by what Tom said really. But I'm wondering if you include in your message things like field of view and some metadata around if it's collimated or not, max and mins of what you're expecting. And I think it's interesting on the units because there's such a wide range of units. You just define that. Otherwise, you're talking loads of different options because you'll still get relative changes. Increases and decreases still mean the same in different units. And whether you also include things like accuracy and variance in your metadata type in your message.
Yeah, you made a good point there. The fact that there's lots of different types of sensor for radiation, and they tend to be calibrated for different levels, isn't there?
Yeah.
It's like if you're trying to measure very low variance of radiation or very high levels of radiation, and have some sensor metadata is probably a good idea. Interesting to see how we can do that without overloading too much information into a message, but we'll have to think about that.
Yes, some basic maximums and minimums and your step values of, and then you start adding. It would enable you to add confidence levels in your maps and things like that. But yeah, that's about it from us, I think.
Cool. That's good. Group 3, which is Cubon, Francisco, Luke, and Paul. Do they have?
Yeah, sure. The things that we really covered was that it's important because there are so many different sensors, but that are going to be quite similar. It's important to have in your standard what the kind of the flag message is of I'm not transmitting this particular data type at this time, because there could easily be a sensor that can do both a dose rate as well as a spectrogram, and sometimes you might not need the spectrogram for your data, so you might configure your sensor to not transmit that message, and make sure having that in the standard as to what those data flags were going to be. Otherwise, it would be stuff that people have mostly covered, I think.
So I guess that would be something like having a compound message type in the message, which has maybe a list of different types of information that could be provided by different sensors, and you just have a Boolean flag that we are transmitting.
Yeah, I mean that could be one way of doing it, is to have a Boolean flag. But I mean, you like in the temperature sensor case where you have the variance, where you transmit 0 in the variance if you're not using the variance field, you just transmit -1s in the data field if you're not transmitting a particular type.
Yeah, that's a good point actually, because I guess something like dose rate, you're unlikely to get a negative value from a sensor. Did you get anything else at all? Anything interesting?
That was mostly my notes.
Oh, cool. Group 4, which is Yannick, Joe, Peter, and Tilly. How'd you get on?
Yannick, would you?
Sure, yeah. So we didn't reach a consensus on what a ROS package, ROS message for a radiation would look like, and mostly focused on discussing the interoperability issues for different sensors that come off the shelf, and then more specifically the difficulty of finding sensor drivers that work with your device without spending weeks or months implementing your own issues. And that is specifically true for the kind of devices that are claimed to have ROS support, and then when you look on their GitHub, you see that they have open issues on their bug tracker that are 4 years old and still unanswered.
Yeah, that's. I think as roboticists in this group, I think that's something that a lot of us have struggled with cameras and things like that. Generally, with different sensors, you do bring up a good point in the fact that even if we decide on standardizing these messages, we still need to have drivers for different sensor packages. But at least if we have this kind of, if we do try and standardize the data that's being sent, the driver should be able to, whoever writes the driver should be able to target this data output and try and standardize it a little bit.
Yeah, we totally agree with you. I think the difficulty is that there is a difference in definition as to what ROS support should mean. For some people, it should mean plug and play. For others, it means it's sort of plug and play, but requires 2 months of hacking and tinkering.
Yeah.
So the definition of ROS support seems to be very broad.
Yeah, I agree with you completely. It's something that's probably a bit out of scope of what we're trying to do here, but I do agree with you completely. And hopefully, doing this discussion and with industrial members here, it gives them an idea of the kind of things that we struggle with implementing these sensors on our robots. But you have got a good point. So are you guys working with sensors on a regular basis?
I do, at Lancaster.
Yeah, and do you have a good idea of the different type? Have you got different sensors which do different data outputs? Like what kind of stuff would you normally get out of your sensors?
Within the RAIN group, we've got like a standard message that we've been using. The detectors that I've been working with are mainly gamma. And I'm starting to get to grips with, or will do, like a neutron detector from the Terrain project.
Okay, and are you already using a standardized message?
Yeah, we already have one. I mean, I'm not sure how good it'll be for other people, but it exists.
So what do you know off the top of your head what it sort of looks like?
It's got, there's a bubble for an overflow. There's an array for the spectral data, 2 fields for the energy calibration, a field for the radiation type, a header.
Okay, so is it a fixed width array you have for the spectrum?
Yes.
Okay, and then I guess the overflow is if the data input is out of bounds over.
Yeah, there's too much. Like it runs over.
Yeah, so it's like overloading the sensor sort of thing. So it's at the top of the calibration range.
Yeah.
Okay, cool.
Part of it, what we talked about, was that the manufacturers of the detectors don't seem to be thinking about robots much.
Yeah, I think it's getting more and more. I mean, I've spoken to people that are making sensors, and they are interested in trying to bring it more towards the robotics side, because there's obviously a big need for robotics in the nuclear sector now. So I think they're moving towards it. But yeah, I agree. It's a bit all over the place at the moment. Is there any other points from anyone who would like to make from that group?
I would have a suggestion to look at the laser scan message and do something similar for the spectrum messages, because laser scanning with the lidars works in a way that it's usually a spinning laser device that has a resolution in angle, so it has an array of measurements for distance, a different array for reflectance, and it has always, it contains the resolution of how many samples are taken during one rotation. So this is quite similar to the spectrum messages we want to reinvent now, and it would be nice to have a similar structure.
Yeah, I'm just looking at it now, and actually, yeah, I think that's a good idea, is taking something that already exists and I guess just change. Don't really need to change too much, but make it more specific to what we're actually measuring. Yeah, that's a good idea. So that's the laser scan message. Cool. If I go on to group 5 now, I think there's only 2 of you left. It's Patricia and Sarah. You still here? Sarah Lonsdale?
Yeah, ours was a very quiet discussion. I think most of the points have been covered already. We were discussing about the need for sort of, you've got to think about what detector you are working with, whether it's a gross counter or whether you've got spectroscopic data. But yeah, I don't know if Patricia's got anything else she'd like to add.
No, not really. I'm from an optics and lasers background, so I was understanding spectroscopy in a different way. But yeah, I think that's fine. A reasonable summary.
Okay, that's all right. I mean, so that's essentially that's feeding back to the idea of metadata of the sensor. I guess there's different types of sensor for radiation, and do we want to collate all of the different sensor types into the same message, or do we want to say there's a spectroscopy message or a count message? But I guess we could think about all of those separately anyway. And the nice thing about ROS is that if the sensor is broadcasting the sensor can broadcast as many messages as it likes, and the network load is only affected by how many you're subscribing to. So we could broadcast a very big message with lots of data in it, and also smaller ones to break it down if you've got different sensor types. So that's something we can think about as well.
Mm-hmm. Yeah, and previously I'd worked with energy harvesting systems whereby they might send out alerts if there's a problem, and also send out each day or twice a day status messages as to like what their norm is, and this was powered by a solar panel, and we had to program the information, the size of information, the frequency of the information according to what might happen. This was for National Grid, and looking at status of pipelines.
So that are you sort of talking about some sort of warning message included within the?
Yeah, like warning, alert signals and warning versus continuous monitoring of steady state conditions.
Okay, yeah. So it fires up a flag rather than continually. Yeah. So I think within the ROS system, there is what's it called now? There's a different type of message which rather than continually publishing, it just flags up. So that is something as well that could be interesting.
You thinking of a ROS service?
ROS service, yeah. Is that right? Or it's kind of like
it's like a one-off rather than like a constant dripping tap.
Like, yeah,
actually, that's something I didn't say. That the ROS messages are kind of like a dripping tap. If you think they just keep going.
Yeah. So normally when you design your ROS driver, essentially you specify the update rate of the message output, and then you can subscribe to listen to it as often as you can, really, or how often as often as you like. But there is ROS services as well, as we said, which is more like an interrupt, where you can basically alert the system without having to continually listen to a publisher. So that's a good idea, actually. Is that everything from you guys?
Yeah, I think so, yes.
Yeah, cool. Sorry. Group 6, which was Joseph, Luke, Louis, and Thomas.
Yeah. The other guys in our group didn't have much experience with instrumentation, being more the robotics side of things. So we mainly discussed the Antec instrument, which is a scanning gamma collimated spectroscopic camera system. So it sort of integrates 3 different sensor types in itself. So we discussed the fact that it's looking at radiation that's not immediately adjacent to the robot. It's looking at things that are further away and using a laser rangefinder distance to them. And at the moment it's sat on a tripod, and we discussed how that once that was integrated with a robotic system that could move around, that the data coming out of it would have to look more like a point cloud rather than like a 2D image. And as it's also spectroscopic, we discussed the nature of the spectroscopic message, which would be an array, and the nature of the image message, which again, an image array.
I'm glad you're here, Joseph, actually, because I remember speaking to you when we were up in around Sellafield.
Oh yeah, Waste Management Conference.
Yeah. So I'm glad you're here as a representative of the sensor industry. So with a collimated, if you can explain just briefly, with a collimated sensor, is that the output that you get, is that a 2D slice, or is that a 3D
So you're looking at assuming a circular collimator, you're looking at a cone of radiation going out from a particular
Okay,
point.
so it's almost like a 2D image.
But over the full 4 pi around you sort of dividing it. The way we've done it is using a hierarchical triangular mesh, which divides the sphere into triangles. But it can be done a number of different ways. And
is that how? So and there's a laser rangefinder. Also,
the distance to the source of radiation, and then extrapolate that back into so it can be overlaid on an image, or as that becomes more difficult as the robot moves around, extrapolated to a point cloud or something like that.
Yeah. Okay. So I think something that Paul, who's also in this workshop, who's also at the BRL, has been working on is using point clouds for radiation data and having points in space. Point cloud, for those who don't understand it or haven't heard of it before, it's a message type in ROS that already exists, which has essentially every point. You can have thousands and thousands of points in space which have an XYZ location relative to the camera normally, and then there's also a color value associated with that, but you could also increase the data on that, so you've got red, green, blue, but then you could also have count value or something like that, I guess, associated with the point cloud. Great. Have you got anything else from our last group?
Well, in this case, what you could do is consider the way it's working with laser scanners. You could have an hemispheric area or something close to an hemispheric area. And what you do is with these laser scanners, you can put a distance. So you have a variable which is distance from the source, from the object. And as you scan around, you can give different informations about all these distances, upon which they say they can attach to a point cloud image, they can attach features. So the features in this case seems to be a radiation level that would be a gamma ray count over a period of time. And I remember when we were in Preston, when I was working on that for indirectly for Sellafield, but also for Leyland trucks, we will reconstruct a scene, and we would around the object or the robot or the camera, and we would be able to give information about all these points, that the ones that were considered for the task. In this case, you could have intensity, and you could have also, as he said, the spectrum distribution around it as well. Starts to add a lot of layers, but you can use matrices, and then with the matrices, it's very flexible. Then you can add block matrices, and you can have layers of information add on to that.
Yeah, So I think obviously the data density gets very, very high as we go on to using point clouds, but it does give us the flexibility and the richness of information, where we can say that this point in space has it's obviously you can use a color image to recognize what it looks like, and then overlay it with radiation information, type of radiation, that kind of thing. So it possibly could be, I guess how do different, if anyone can help out here, like how do different radiation sensors fit with that? Do you need to combine sensors to be able to give us that point cloud information, or can we work out that information just from any sensor type? I guess not.
My take is you would need at least 2 or 3 sensors to infuse this information on this point cloud, and derive a mesh which can be handled by the memory of the microcontroller, if it is the case.
Yeah.
The question would be whether the robot can physically move to every coordinate in the point cloud and make a recording in situ, or if you want to have a range standoff kind of measurement where the radiation sensor is mounted on a turret and just scans an entire room, for example, which is a completely different order of complexity for a problem.
Yes. Yeah, it's got more complicated as we've gone on, which is good, but
well, it has to have a certain level of complexity, because if you want to send a drone inside a nuclear site and determine the different points which need standing first. So in terms of, I'm going back to the task because this is what I worked on. It's a task-based, and then you derive the sensors, you go for the sensors, you go meet with the people with the sensors, and then you attach the sensors to that robot. And then you start defining paths, where it be a pan-pit system, that's a path, but then it's a fixed point. Or if it's a drone, then you are going to send something that is going to change pose and position and heading, and you're going to, again, derive a point cloud of information, which is then you're going to attach the sensors that you have there, and you're going to attach that to the information that you get, the geographical information that you're getting.
Yeah, so there's a point here where do we want to just provide the basic information of the sensor, which can then be combined with other information that's collected on the robot, such as, you know, when you do navigation, robot navigation, you collect the sensor messages and then they are combined at a later point in a different ROS node to create a view of the environment that you're moving around in. Do we want to be creating a point cloud in this point, or should that be for the software engineer essentially to create the data that they need to? Should we just be publishing just the pure data, or do we want to do more complicated stuff within the ROS message?
Well, what do you find as the pure data? Because the problem with radiation measurements is that the robot itself acts as a attenuator, as a shield of radiation. So it's not like making let's say, a measurement of a relative humidity, which the robot does not generally influence. So no matter where you put the humidity sensor on your robot, you will generally always get the same value. Whereas the robot itself will attenuate radiation because it has a finite mass and obstructs the radiation pathway. So if you want to channel correct radiation data, then technically you would have to take the entire robot model into account to calculate an attenuation pathway from every possible direction. And this is also one of the reasons why, as suggested before, often surveys on drones are being done, because then the radiation sensor is mounted under the drone, and you have a clear line of sight to the entire ground floor kind of thing. Whereas if you mount it on a tracked or a robot, then obviously the robot will attenuate radiation from one side. So the question is then, do you want to incorporate like a step model of the robot in this message preprocessor and reverse attenuate the radiation levels at that point in the calculation, or do you want to push that further upwards?
I think there would have to be, I mean, this is just from my experience, I think it would have to be further up. Yeah, so as Andy said, this is more to do with if you buy a sensor and then you plug it into your system, does it provide all the information you need so that your higher level processing can then do that kind of thing? So that's really interesting. The fact, I'd never thought about the fact that the actual robot itself could affect the sensor values, but I think that would have to be configuration specific, and what we're talking about here is just the data that comes out of the sensors. What's the best way that we can almost generically represent that for anyone that wants to use a sensor? They can use it plug and play is the kind of the idea.
Well, I think it's a very interesting problem, because there are many ways to solve it. Like, you can make the robot, if it's like a wheeled robot, you can make it like do donuts all the time, so it sees radiation from all directions, and then merge all these different measurements in each direction together to kind of cancel out the effect of the robot itself. Then you would have to go for very specific movement patterns that are slightly different from the normal, snake kind of movements. So making accurate radiation measurements typically involves more in-depth control of the robot's movements and awareness of the robot's materials even. Because things like the battery pack...
This might not be used on a robot at all. It could just be part of an autonomous system. Could be, like one of these gate, like vehicle inspection systems, or, so I don't want us to get too caught up with how you correct the data. Because, for example, if you collimate your detector, then suddenly there's a spatial, there's a spatial component. As you mentioned, if you have self-shielding by the robot, or even this could be part of a backpack, with something running, in which case humans attenuate the signal as well. So as long as we have a method of, being able to get that sensor to talk to whatever else is in the system, I think that is the priority. And in terms of doing corrections afterwards, I think that would be up to, because let's face it, there are plenty of people who wouldn't consider doing that kind of correction, or perhaps it's not necessary in their application. But you do make a very good point that actually what we need to provide is enough information that can be used by the next node down, which I think is kind of what you're trying to say, or that's the impression I get anyway.
Yep, that's absolutely correct. I have no idea on how to materialize that kind of information at this point.
Yeah.
Thank you. This is what this discussion's all about. So yeah, that was useful.
Can I jump in quickly?
Sure.
Yeah. So I've been working with the sensors and alongside Oxford Robotics. And alongside with them, we've been putting sensors like the gamma detectors onto Huskies, and then building point clouds off that with a collimator. And the point clouds have been done kind of processed at the same time, using just the data being spat out from the detector.
So do you, I guess, in your sensor driver, you actually build in the point cloud calculation?
Nope. The detector just produces the radiation data.
Yeah.
And then there's another node running at the same time that pulls it all together with a point cloud and kind of colors it as it goes around.
Yeah. So I guess you've got various sensor inputs coming into that point cloud node, which then collates the information into a point cloud.
Yeah, and it seems to be the most flexible because I don't have to adjust the radiation code to deal with a different robot or a different application. I kind of leave it up to robotics experts to deal with the point cloud.
Yeah. Yeah, I think that probably makes more sense. Because a collimated sensor gives you the information about what it's pointing at, and then what you normally do in the same way as you would do with navigation or something like that is you would take information from the robot of which direction it's pointing, and rather than trying to do it all from one point, that's the idea behind ROS generally, is that you've got sensors spitting out data and then you can subscribe what you want to. So I think, is there anyone else anything interesting they'd like to thinking about at all? We've got quite a lot. What do you want to do, Andy?
So one thing that actually someone put in the chat, I'm going to find Francisco. I think Francisco Garcia added this. That actually we're not the first ones to have a crack at this. So they linked a publication where people have tried to. So there's already a data. So I did know about this actually. That there's a data format standard for radiation detectors and radiation instrumentation. So what someone's then tried to do is then try and mesh that into ROS. I wasn't aware of this document actually, that someone had tried to go into ROS. So this is very interesting. And actually a lot of the stuff that we've mentioned here does come up in that document. I think you could do things better where they've maybe gone a bit over the top. What I would say is really, hopefully we can come away with a a message structure or a couple message structures. If anyone would, we're starting to run over time now. So if anyone would like to continue this discussion, I think I know that people might have to disappear. So please get in touch. My hope is that we can actually put a message structure or a couple message structures or whatever it might need up on GitHub or whatever, and people can start using this because at the moment there just isn't really anything, and it's taking a bit of time. I think this feedback is really good. It's brought up some things that I certainly had not thought of. Also, actually, we're really starting to think about like what this data feeds into, which is a really important thing as well. For a lot of the current implementations, it's really just taking counts, then maybe doing something, and then people are doing their own bits and pieces with that. But maybe we should be a bit more sympathetic to like what's happening later on as well. The metadata, that came up a couple of times. Same thing with the tick has sort of been brought up 2 or 3 times. Yes, I think this makes sense, particularly maybe things like min and max or some sort of calibration, either in the message itself or in or on the ROS parameter server. We can obviously try and standardize what should be included or not. This then sort of, is it a single measurement or is it a spectral measurement flag? We had sort of, I think we had more points saying that it should be in one message, but some people were sort of saying maybe it should be differentiated. I'd like to sort of have a further discussion about that. The way I see it, I think this is probably, if we were to make, so interesting that no one really mentioned splitting messages based on units. It seemed to be sort of more on the format of the data. So is it a single measurement or is it a spectral measurement? Which was I wasn't expecting that. So yeah, that is something that I would like to also discuss further if people want to be part of a further conversation, basically. So yeah, if you do want to be part of that, please feel free to email myself. So that's andrew.west@manchester.ac.uk. That should be in all the Eventbrite stuff that you've seen, or you can email Alex, who's alex.smith@brl.ac.uk. And it might be that this is rather than meetings, we might have we'll set up like a, not Slack, but something like this, right, where we can, or even maybe that, where we can have a bit of a discussion and come to some agreement, and then we can put this out to the world.
Yeah, so I think this what's really nice about this group of people that we have is obviously there is a lot of academics, but we do have some people from industry as well, which we are sorely missing a lot of the time when we're talking in academic discussions. And having the feedback from people like Joseph, who's at Amtech, who are producing these sensors, really helps us work out what we're going to be using, and also feeding back to you guys on the kind of stuff that we need in our when we're looking at sensors. So it would be really nice to continue this discussion as we go on. I think originally, Andrew, we did talk about making this a 2-day thing and possibly doing this again in some point in the future, but we'll see how it goes. I think if we've got enough interest in general discussion with the Git and possibly a Slack or something like that, then we can continue like that. But we'll hopefully, the idea is to keep this rolling and keep the dialogue up between the industry and the academics.
Yeah, and what would be great is from people to sort of test this, right? So when we get a standard together, actually put it on some real instruments, and does it actually deliver what we hope it delivers? You know, some of you are already communicating with radiation instruments. Hopefully, moving over to a different message structure won't be too difficult. Other things that your sensor just can't provide. You know, are there data fields that are going to be missing? Other things that end up being superfluous or just not, you know, where does it fall down, right? Because we want this to be hopefully as flexible as possible.
Great. Shall we call it? Anyone?
I think so, yeah. Thank you very much, everyone, for coming along. Yeah, this has been really helpful because everyone's just been working in their own bubble. And like Tilly mentioned earlier, she went to Oxford. I know a few people went down to Oxford, and they all met up in Bristol and what have you, and then realized that none of this stuff sticks together. None of it's ready to go together. So yeah, this is hopefully this is the next step forward. So thank you very much for joining us today. If you have any questions, once again, feel free to email myself or Alex, and hopefully, yeah, if you want to continue this, yeah, just let us know, and yeah. Thank you. Go have some lunch. Go enjoy some sunshine if it's sunny near you. It was really hot in this office, so I would be glad to be done.
Cool. Cheers, guys.